Period. We'll take a look at the lab. So we're going to first talk about what's called the continuity equation. The continuity equation has to do with flow rate. We'll talk about Bernoulli's principle. Bernoulli's principle is responsible for airplanes without wings. The effect of Bernoulli's principle is responsible for airplanes. But Bernoulli's principle obviously is just stating what's already existing. But the pressure differential we'll talk about there. And then we'll talk about turbulent and laminar flow, which you've probably heard already, right? When you hear turbulence, what do you think of an airplane? When you hear turbulence, shakiness, right? Bumps, yeah. Okay, same idea you're going to see here. So let's begin with the first slide. Let's start with those definitions, actually. Let's start with laminar, turbulent, viscosity. Viscosity, fine. Where's Joe? There you go. And then ideal fluid. So those four terms. So first, laminar has to do with flow that is predictable. So if you've ever seen a stream, like a very calm stream, meandering down the path using gravity for its water to actually fall, that's laminar flow. But how many of you have gone whitewater rafting before? Anybody? Okay, come on. When you see the eddies, the white like churning of the water, where it gets all foamy, that's turbulent flow. It's irregular, unpredictable fluid flow, usually caused by some sort of obstacle in the way, or some sort of change to the actual flow, whatever that fluid is. So maybe suddenly you have all this fluid flowing, and then a gate starts closing, right? A valve. That's how you mean. When you turn your sink on and off, what are you doing? You're physically, take a look. You're literally doing what I'm doing here. When you turn this on, you're opening a gate. And as I open the gate a little bit more and more water comes out. So changing the fluid flow itself could usually cause turbulent flow. Now we're going to talk in this class about a certain number that we use to characterize flow as either laminar or turbulent. Because this is very theoretical right now, right? Like smooth flow is laminar. Turbulent flow has to do with the churning and being unpredictable. But how do we mathematically put a quantity on that? And we're going to talk about a certain number that is used to describe whether an object flows in a turbulent or a laminar way. Now to do that though, I'm going to talk about the number in a second. Let's talk about these two terms first. So we talked about viscosity before. This has to do with the friction that's actually internal in the fluid. Think about fluid for a second. If fluid is flowing, the fluid particles themselves rush past each other. Right? That's what fluid is. A fluid is a gas or liquid because its molecules can readily flow past one another. So when I literally go like this, the air particles, some of them might be going faster than others. Literally, as the air goes out of my mouth in this direction, some of the particles are moving faster than others, so you have these slipping occurring that are happening between them. Imagine, this is a good example. We didn't do one of these much this year. You get an example where we stack two objects, right? We talked about normal force, how it changes. But imagine if I had these two erasers, okay? I'll do it up here actually so we can see better. I have these two erasers, and I pull on the top eraser. If I just pull on the top eraser, the whole thing moves though, right? Why is the whole thing moving? I'm just pulling on the top eraser, up, and now it's not, right? Now just the top eraser moved. But if I push down a little bit maybe, and pull, now the whole thing is moving. What's the difference between that and then where it actually separates? What's physically happening that keeps it together? Friction between, very good, simple. Friction between the two objects. So imagine each of these objects as a molecule of the fluid. As this molecule of the fluid rushes past this one, what is it going to do? As it rushes past the other one, it's going to naturally
create friction.
Yeah, and it's going to kind of pull on it a little bit, right? That's viscous force. That's what we've been talking about the whole time. That's what viscosity is. Okay, it's this idea that there's internal friction between the molecules. So, ideal fluid. Ideal fluid is what we are considering all of our fluids to be. They are considered to be, we use this phrase already, incompressible. They cannot be compressed. We consider them to be non-viscous. So water is not a very viscous fluid. If you were to pour honey out of a jar, what does it look like when it flows? It flows real slow, right? That's a very viscous fluid, honey or molasses. And then the last thing we're talking about is that the flow is non-turbulent. So when we talk about water flowing through a pipe, we assume all three of these things. So if I suddenly poured a vat of honey or molasses down the drain and thought it was going to flow out the drain in the same predictable way we would assume using what's going to be called the continuity equation and the Bernoulli's principle equation, they would not be true for this kind of a material like honey or a material that, or a flow that is turbulent. So we are assuming these three things for all of the following mathematical concepts that we're going to study. Okay, those are big assumptions to make, because when that's not true, the math is far beyond what we learn even in college. It would be graduate level stuff. Okay, so in college, when I studied this, we assumed these three things. Okay, and it used differential equations and calculus. In grad school, when I took thermal fluid systems, we did not. And it became a lot more difficult, and you use a lot of programming to solve those problems. A lot of fluid mechanics is not solved by math by hand. A lot of it is done using simulations and writing programs to do it for you. So I use programs that did what's called computational fluid dynamics. It's really cool stuff. Imagine, right? Imagine there's a certain amount of fluid flowing. The program would literally show what the fluid would look like using all the equations of motion. And you can see a perfect simulation of this. We're going to use an atom law that does something like this. It does something very much like what computational fluid dynamics does. But a lot of this stuff is using that assumption there. Now, the number we're going to talk about, and this number is like a threshold, right? Like the critical angle, remember for Snell's law? The critical angle was the angle at which if you exceeded, you had total internal reflection, total internal refraction. We're going to talk about a threshold number, so jot this word down. It's called the Reynolds number. R-E-Y-N-O-L-D-S, the Reynolds number. I'm not going to go into the formula for it. You can look up the formula if you want. The formula involves a couple things you haven't learned, that's why I'm not going to go into. The formula to determine the Reynolds number matters, or is based upon the density of the fluid, the velocity of the fluid, the density, the velocity, the viscosity of the fluid, and depending upon what it's flowing through, the geometric makeup of the pipe or whatever it is that we're looking at. Okay? So that's not something we can really characterize, because you can say the diameter or the side length, so some geometric part of the actual pipe. Now, it's good to understand that those things affect the flow, because think about it for a second real quick. If I have a much narrower pipe, the flow is going to change versus a wide pipe, right? So it might go from laminar to turbulent based on the actual narrowing of the pipe. If it's a very dense fluid or a very viscous fluid, it changes whether it's turbulent or laminar flow. So this Reynolds number is a limit. Below the Reynolds number, or below a threshold, it is laminar. Above the threshold, it is turbulent. Again, using the Reynolds number, calculating the Reynolds number allows us to determine if it's laminar or turbulent flow based on whether or not it is above or below a certain threshold. That threshold is a function of the setup though. So let's say the number is 10,000. Okay? The number is 10,000, whatever flow it is, happens to be in a pipe and stuff. It's not water in a stream, so it's different numbers. And you get an answer for your Reynolds number of 9,000, it means that it's laminar still. The flow is not considered turbulent. But anything above 10,000 is considered hypothetically turbulent. So we are really going to be talking about the theory behind this, not the actual math. Yes? Okay, the theory behind it. It's a threshold. That's a good way of thinking of it.
You said that water is very
non-viscous.
Is it completely non-viscous?
No. It has viscosity.
Is there anything that is completely
No, because everything has friction.
Yeah.
So any gas will have viscosity, but below a certain amount, we consider it to be a non-viscous fluid. A lot of assumptions, right? We do a lot of modeling in physics, so we take concepts and model them to make them a little bit simpler, right? To make it more simplistic, like when we know air resistance for projectile motion, right? We say there's no friction there, but there's clearly friction. Same concept here. There's always going to be viscosity in any fluid flowing, but it's a matter of how much is there, actually. Let's go on to the continuity equation here. Continuity equation is one of the easiest ones you'll read about. It really is. Okay? One of the easiest ones. Concept is this. If you want to know how much the volume of flow is through a pipe, just look at the cross-section of it. This is a volumetric flow rate. Little v, though, is velocity. Because this is a volumetric flow rate, a lot of students get confused. Little v is velocity. Let me explain why it's a volumetric flow rate. Use your units, please. What are the units of area? Units of area. And units of velocity?
Velocity, meters per second.
Meters per second. Very good. So this yields units of cubic meters per second. That's a volume that's flowing at a certain rate. Volumetric flow rate. Again, volume is meters cubed, right? So if I take area times velocity, I get units of meters cubed per second. Meters cubed is volume, second is time, so it's volume over time. Volumetric flow rate. Volume over time. So if you want to, put this at the end. It's not on your equation sheet. Okay, where V in that case is the amount of fluid that's flowing in a given time period. So gallons per minute. Gallons per minute. Where have you seen that before? You've seen it at some point, I guarantee you've heard this phrase of gallons per minute. Or liters per minute for those that maybe use the metric system. Yeah, very good. Gas stations. When you pump gas, it's flowing at a rate in gallons per minute. When you use gas, you use a certain rate of gas in like gallons per mile. Or you could say gallons per minute if you're going at a constant velocity in the car. Gallons per minute is an example of a volumetric flow rate. Gallons is volume. Minute is time. Gallons is volume. Minutes is time. Same thing as this. Same thing. Cubic meters is volume over seconds, which is time. So what does this tell me? What does this tell me? Look at the equation. Look at the scenario. Somebody give me a generalization I can write. It's not obvious, so you might have to do a little bit of quick just looking at it. Yeah.
The flow rate's going to be equal from unit to
Good. The flow rate, which is what this is defined as, is always equivalent. Very good. The flow rate is not going to change no matter where we are. And that comes from this word right here also, right? Constant. Very good, Rick. What else do we know? In this diagram, maybe, or maybe a generalization. You could say, as this changes, this changes. Give me those blanks.
The area that the fluid is flowing through gets smaller, the velocity gets bigger, and it's...
Very well done. That's all, and vice versa. Very good. That's exactly right. Good job. They are indirectly related. As the area goes up, the velocity of the fluid will go down. It will go down. Okay, in a fixed system. In a fixed system. And that makes sense if you think about it. If this is some number, right, we start the pipe with a certain area right here, and a certain velocity right here, and we start it right here. This is going to be a number, right? If this is a number, say the area here is 20, and this is 5, 20 times 5 is 100. If I suddenly go from 20 to 50, that's going to go to 2, right? So this goes from 5 to 2. So they're indirectly related. Indirectly related. Okay? Think about like a faucet or a garden hose. These are just the prime examples of it, right? A garden hose. If you've ever taken your thumb, you're going to say, yeah. Take your thumb and put it over a garden hose. What happens to the water suddenly? It shoots out much further than the garden hose. Because what's happening when you narrow the area? Less area means more velocity. More velocity means it goes further. It's logic, right? It's almost logic. You've done it as a kid. If you've ever watered your plants in the house or in the backyard, forget not everybody's suburbs, but if you live in the city, maybe on a balcony. But if you use any sort of a faucet and you put your thumb over the end of it, you can literally do it with this one if you haven't done this ever in your life. Turn the sink all the way up and just take your finger and put it over the edge. And you'll see the water velocity will shoot out when you do that.
When I was like 6 and I was doing that, I thought it was because like the water was pressure.
It is pressure that's doing it too. We'll talk about that. Hold on. You can go a couple slides ahead and see if you want to see that. But it absolutely is pressure that causes the continuity equation to be true. It all comes from pressure, yes. Absolutely, there we go. But Rodrigo, what's interesting here is that this is a nice phenomenon to use, right? The fact that the volumetric flow rate is constant comes about, but the pressure is what's causing the change in velocity due to the area. And we'll talk about that in a little while. Absolutely, it's pressure, yep. Very good. Let's sample first before we get to the concept of pressure, okay? So let's start with this example here. Now, just like with the hydraulic lift, sometimes you're given the area of the piston, but some homework problems, if you looked at it the other night, right? They gave you not the area of the piston, but what? The radius. So this is not giving us an area. Is that clear? Do you see this right away? I'm given a radius, that's all. So in this problem, the formula is A1V1 equals A2V2. But what are you going to replace A with, obviously? Which is? Pi r squared. Very good. So let's list our givens. Water flowing through a pipe with a radius of 4 centimeters.
Is that V or no?
R, that's R. R. And V, and you look at the units, right? And V is 5 meters per second. The question is, what should the radius reduce to for the velocity to double? So what's the new velocity going to be? 10. Okay. See how I'm writing this, by the way? Take a look. I can write 10, or if I want to be fancy and use a little bit of general solutions, I can write double V1, right? Because the problem said it doubles V1. So I can literally replace V2 with 2V1, or I can just put a 10 in its place. Either one, right? Either one is fine. Okay? My equation for this is the following. Now do you see why I might use this instead? Take a look. I'm probably going to use this instead for V2. Because if I move this in for V2, what happens on both sides? What happens on both sides? Yeah, V1 cancels. So instead of putting a 10 in for V2, I'm going to take the algebraic approach and plug that in for V2. And this equation becomes A1V1 equals A2 times 2V1. V1s on both sides cancel. This makes sense. This makes sense. If the velocity doubles, what will happen to the area? It will halve. Again, if the velocity doubles, what will happen to the area? It will halve. Be cut in half. So if I knew the area, hypothetically the original one, say it's 20, I just divide that by 2. I get the first area, the second area, right? Put a 20 in here in your mind. Put a 20 right here. Divide this by 2. The new area is just 10, isn't it? Again, I'm doubling the velocity so the area should halve. But am I finding the area? Joe, am I finding the area? What am I trying to figure out, Joe? What's my unknown?
Your unknown is the radius?
The radius. So I need to go ahead and do this. Again, this 2 does not go away. This 2 carries down right here. So the reason I point this out is because the radius will not halve. The area halves if the velocity doubles for sure, because area and velocity are indirectly related. But the radius will not be cut in half. Why? You can see it. Why is that? Why is that, Rick? Because it's squared. Very good, Rick. It is squared. It is not like area that is not squared when related to the velocity. So it's not going to just nicely halve. So let's cancel pi on both sides. Cancel pi. Right? For those that did the homework last night, that were able to get it done, for those that still have to do it even, notice that pi cancels on both sides for this and the hydraulic press. Hydraulic press is F over A equals F over A. While the A in the bottom, if it's a circular piston, is pi r squared. Pi's in both denominators cancel. You picking up on what I'm saying right now? Does that make sense? Pi's cancel on both sides. If it doesn't, please ask. So in this case, if I want to figure out what R2 is, I'm going to divide by, so here's R1 squared. I'll divide by 2 on both sides, and then take the square root. Again, divide by 2, get rid of this, move the 2 over, and then get rid of the square, take the square root to get R2 by itself. Now, Again, I'm doing a lot of algebraic stuff. For those that don't like the algebra right now, where should you be working? Up here at the top, okay? Right here. If you don't want to work with the algebra, that's absolutely fine. At this point, for V2, plug in a 10. For V1, plug in a 5. Figure out what the area is from this radius. Plug that area in right here, and you could solve for this area. Once you know area 2, you could set that equal to pi r squared and figure out what the radius 2 is. So if you don't like this algebraic approach, plug in where it's red, please. Yeah. Or where it's...
Is it the square root thing just the hour?
Yeah, but the 2 in the bottom doesn't get rid of it, right? Don't forget about the 2 in the bottom there.
But then what happens?
So it becomes...
You can't do it then? Oh,
Right? Because technically, isn't this really...
yeah.
Right, that's what it really is. When you take a square root of a quotient, you're taking the square root of the top and the bottom. So yeah, Rodrigo, you're right. This square root of r squared cancels, doesn't it? Becoming r1. Yet we have a radical 2. So what can we say? Well, if the velocity doubles, the area halves. But if the velocity doubles, the radius goes down by a factor of radical 2, not 2. You see the relationship here? Because it was squared, it's the opposite inverse reaction. It's like a square root instead of a square there when you're solving. So again, the velocity doubles, the area goes down by a factor of 2. But if the velocity doubles, the radius goes down by a factor of radical 2 because it was squared. We'd have to get the square root to solve it. Either way, solving it here, we're going to get the same number. R2 will turn out to be 0.028. And those units are meters. So I'll write it as 2.8 centimeters. 0.028 meters. That's a little meter symbol here. Either way we do it, whether we plug in here, or back up here at the red stage. If you're plugging in the first line and you can't solve for radius, you need to get help with it. Whether it's coming to see me or just practicing it. It's one or the other. Okay, again, because if you solve what's in red, you would end up getting A2, right? That's what you'll get. But then you got to find the radius. You got to get whatever your A2 is and set it equal to pi r squared and solve for radius. So if you're going to do it in red, you got to still be able to solve for radius, obviously.
Is it okay if you kept it in originally kept it in centimeters and just got 2.8 anyway?
In this problem, it's fine, James, yes. But in some other problems, that's not the case. So if you want to remember that it's okay in this problem, that's all right. But it's not true for other problems. Okay? It's not always true. You can keep units. But because centimeters are in both circumstances, it'll be fine. Okay? But if you're using something else, like another formula earlier in the year, like for example, work equals FD cos theta, D has to be in meters there. Absolutely has to. In this problem, it doesn't because we have both sides of the equations with the centimeters, so it kind of balances out. That's why it doesn't matter here, James. That's the only reason. I saw another hand. Fiona? One of you guys in the front had a hand? No? I thought I saw. Joe? Go ahead.
I was going to ask, this is kind of a side question.
Yeah?
Do you know the most viscous force? I
Like fluid? I have no idea, Joe. I have absolutely no idea. Is that what it is? You looked it up?
It's on the chart right here.
Yeah. I don't know where the chart is from, if it's actually true. But yeah.
Well, out of all, comparing water, milk, oil, light syrup, heavy syrup, and chocolate.
Oh, yeah. I mean, comparing those only, Joe, sure. That's a relative statement you're making, though. Chocolate syrup is more viscous than the water, fine, but it's probably not the most viscous fluid out there that exists. I have no idea, Joe. I have absolutely no idea. Next. Sorry, Joe, I just really don't know.
Tar pitch.
What is it?
Tar pitch.
You just looked at?
Yeah.
Is that what you said, tar?
It's chocolate syrup.
Tar pitch makes sense. It's pretty much magma, right? Magma? That's what tar pitch is. Molten rock that's flowing. Okay, now, listen. Rodrigo had a great question before, and he said, I thought when you put your thumb over the end of the hose, you make the outlet smaller and it just builds up the pressure. And that is what's happening, actually. That's physically what's happening. So let's look at this diagram here. What happens is this. When there's a cross-section that's tapered, smaller, write that down, please, tapered. So it's a word that you should know from physics. A baseball bat is tapered. right? The actual meat of the bat, the barrel is big, and the handle is rather small for the bat. It's a tapered object. Firefighters, when they have to shoot water up to the 3rd or 4th floor, what do they do to the nozzle at the end? They turn the nozzle, and it makes it a smaller cross-section. The water shoots further up, just like the continuity equation showed us a minute ago. It's because of Bernoulli's principle. Bernoulli's principle tells us that as the actual cross-section itself decreases here, what we have is an increase in velocity. Well, how is that possible to have an increase in velocity? What causes velocity to change? What one word? One word, change in velocity, is really defined as acceleration. So let's talk about this. Ready? If the velocity is increasing as this leaf flows through the pipe, it means that there must be acceleration to the right. If that's true, there must be a net force to the right. And since pressure is force over area, there must be a net pressure acting to the right. And that's shown here. P1 is greater than P2. There's a pressure differential. Why do you think when you guys open the window, I tell you, let's open the door also? Why is that? Why do we not just open up one single window? What's the reason for it? You got airflow. It's the difference in the pressure from outside to inside. Now, if the air's flowing in the room and we have the other window open, it'll work pretty well still, right? You have the pressure out there that's higher, the pressure here that's lower, the pressure out there that's higher. So the pressure differential causes the air to flow inward. Now, when we start talking about thermal systems, air flows from hot to cold, hot to cold. So if it's warmer in one area, it'll flow inward. If it's cooler, it won't, but you can still feel like it's hot, cold air coming in the window. The reason it feels like cold air is because cold air is rushing to the bottom, hot air is rushing out the top, and you have a convective flow. We'll get into convection and heat transfer in the next chapter, actually. But to give you an idea behind this, it's pressure differentials that are causing your door to slam. Has that ever happened to you before? Ever get freaked out? Say you have the front door of your house open on a nice day, and the windows are open in the backyard, or going to the backyard, and the front door just slams shut on its own, or you wonder, how is that possible? It's pressure differentials. It's physically what's happening. In an airplane, when a window breaks, you saw what happened recently, right? Did you guys all see that flight? The lady got sucked out the window, got pulled back in, and ended up dying. She literally, the engine failed. It caused the window to shatter next to her. She literally got sucked halfway out the window. They caught her, held her in the window. This is no joke. The pressure inside the airplane is far greater than outside an airplane. When you're in an airplane at high altitudes, there's very little pressure because there's not a lot of atmosphere acting down on you. Less pressure outside, more pressure inside causes air to flow out. So she physically got sucked out the window. They caught her, pulled her back in. This is no joke, pulled her back in, but she ended up dying from internal bleeding, I think is what it was.
Because it doesn't crush you, the window's so small.
Well, no, it doesn't. Joe, the window is not too small for you to fit out. The problem is that in the process of her getting sucked out, I think she had some damage and some injuries that caused her to get internal bleeding, and they couldn't revive her. And actually, I think if you look at the article, I think there was even a doctor or a nurse on board.
Did it break your seatbelt?
Say again?
Like the seatbelt didn't jam?
I don't know much. I don't know much about the seatbelt. Did she have it on? Yeah. I think it pulled her literally I mean, the seatbelt probably helped her to stay in partially, but I think it sucked her pretty much right out the seatbelt. Yeah.
You know those programs about what to do in these situations and stuff?
Yeah.
You know, if your car goes off the bridge.
Listen, guys. This is cool. I watch these videos all the time.
Yeah.
Survival videos.
Yeah.
Yeah, I love them. Yeah.
Like,
And it's all science, all survival videos.
if you're in a car and you fall off a bridge to water, and you try to open your door while the car is halfway in the water, you won't open it.
Why?
So
Because there's a lot of.
pressure.
So?
You have to break your windows, let the water flow, and once the car is entirely in the water, you can just open it.
Yep. And here's the thing. First of all, there's several things. You should take your seatbelt off. I know it's crazy, but people won't tell you that. But seatbelts get jammed. If you're not falling too far and you're falling into water off a bridge and you're in a vehicle, believe it or not, you should unbuckle your seatbelt. I know it's crazy to think about it. Because you think, I'm going to smash into the windshield. You probably will, and you'll probably still do it, but you want to be doing this, and have your head down, and your arms on the actual dashboard. I know you're not thinking this as you do it, but instincts might kick in. You unbuckle, head down. You're going to get the airbag that's going to hit you to stop you from getting hurt. You'll probably damage your arms dearly, but I'd rather take 2 broken arms than drown, right? But the seatbelt is the thing that gets caught a lot as well. But the window's huge. That's why in windows now, what do they have? A lot of cars. Ever seen the little survival kits? The survival kit has 3 things in it. What are they? One's a window breaker with a very, very, very fine point, which has very, very, very little area, which means it has very, very, very high pressure. See how they're all related? The little thing, it's literally, it looks like a little pickaxe. It looks like a little thing that comes to a conical point, and you smash it into the window and it breaks right through the window. That's one thing. What's on the other end of the device? Seatbelt cutter, that's 2. What's on the third thing? You got it? Flashlight. Because if you start going underwater, you need a flashlight to get out. I know I'm not trying to scare you, but if your car is sinking to the bottom of something like an ocean, and you'll get so disoriented you won't know which way up and down. So a flashlight will really help you in that circumstance.
I mean, if you're like deep enough where you can't see the surface, how would you know?
That sounds like a whole lot.
Well, hopefully you can see either the bottom or something else that will tell you if you're falling up or down. You have the flashlight on, you can see which way the car is physically moving, you go in the opposite direction. Right? I mean, that would be the logical thing. Anyway, yeah, I mentioned in those videos too. They're really cool, right? It's all science. There's a couple, I watched one literally 2 days ago on like a retired CIA expert or retired like, what are they called? The ones that work for the president. Secret Service? Secret Service retired guy that talks about like how to escape someone if you're being held up and you know you're in a locked trunk and you're going to get killed for some reason. Say you're being kidnapped and you know you're going to die. Like, what are you going to do? How could you get out? Stuff like that.
Have you ever
There's a lot of stuff.
Break the light.
The what?
Bear
Grylls, yes. Well,
What causes like the seatbelt to get jammed?
I don't know. I've never read into it, but I know it's one of the big problems when you have an impact, the seatbelt can get jammed. I know that the seatbelt mechanism locks automatically when you have impact. That's because it doesn't want you to go forward, so it has a mechanism to lock. Maybe the lock is jammed. I don't know. We talked about it physically. Remember with the piece of metal into the car? I don't know why it gets jammed.
Yeah, there was actually an episode in Whiteboard about like what would you do if the car gets like sunk, and like he did it in a pool, so it wasn't like that.
Yeah.
That much.
Hey, you do it in the pool, man.
But like basically what happened was that like he tried to like open the door, but like the door wouldn't open, so eventually he would have to wait until the water reaches a certain level, so the pressure just like opens the door, and then that's how he because after that's what he did, like because after a while the pressure is so great that like the door won't open and he like just tries to like, push on it. Whatever pressure inside.
The pressure outside is extremely great. Well, the pressure outside is extremely great. You're saying that he was able to overcome that pressure once it was deep enough?
Like once the water reaches a certain level in the car.
In the car.
Yeah, in
yes,
the car.
yes. That's what he was talking about by lowering the windows so the water's flowing into the car. But the best thing would be to literally lower the windows as you're landing. Right? If you had the windows down and the car is landing in the water would just rush into the car and fill it up. You wouldn't have that pressure, you could swim right out the window. But yeah, once the water's in, the water pushes back out. Absolutely. It's a balance of pressure that you have. Yeah, you would probably be able to then open the door. That makes sense. That makes sense. So you breathe for a while, stay calm, breathe until the water's up to here, then you get the door open. Oh yeah, because you use up all the oxygen. Yeah, that's the guys. That is number one thing: is stay calm. Use up the oxygen in the car, right? If you're frantic, you use more oxygen. Got to keep it cool. It's not easy sometimes. All right, next slide. So again, right, unbalanced pressure, more pressure behind, less pressure forward. So an unbalanced pressure causes the water to speed up. Unbalanced pressure causes net force, causes acceleration, makes the velocity increase. The last slide is our application, our application for today. It's our application. Can somebody read this nice and loud? Joe, why don't you read it? You got a good voice. Nice and loud, Joe.
The force on an airplane wing can be explained using
Bernoulli's
principle. Airplane wings are designed so that the airspeed above the wing is greater than the airspeed below the wing. As a result, the air pressure above the wing is less than below the wing. This imbalance of pressure creates a net force in the upward direction known as the lift force.
Yeah, so the velocity on the top, the velocity on the bottom, right? The velocity on the top of the wing is greater than the velocity on the bottom of the wing. And what we just said was when the velocity is increasing or more on one side, it's got less pressure. So the pressure up here at the top is actually less than the pressure at the bottom. This is the key. If there's more pressure at the bottom, it means that there's a net lift up. Hence, lift force. Lift force. Again, more velocity on top is less pressure. More pressure here, less pressure here. The net force acts in the action or direction of that red vector. That's the direction of the force because of the pressure. Yes?
Those first airplanes that have like the wings like this, like the same. Or not?
They did not have the right pitch that they should have. So if you look at airfoils, and if you look at an airplane wing when you're lifting off, the little rotors on the side of the wing adjust their pitch. Have you seen that before? They literally adjust as you're lifting off. Once you're cruising altitude, they change. And then when you're landing, those flaps all drop down to create more friction. So they weren't adjustable, but the same principle was used. The same principle was used. But they were not as adjustable as today's airplanes. Probably. I don't know. You're talking about like the Wright brothers?
Yeah.
I'm guessing they must have used this principle. They had to.
Because they look like red.
But they had an opening in the middle, remember? It was a plank, another plank, and those planks were kind of connected. So the air was flowing below and above one, below and above the other. So it was really like they had two sets of wings. See what I'm saying?
Yeah, but it was like straight. It was straight.
Yeah, they weren't tilted is what you're saying, right? That's what I'm saying. I'm talking about the angle that changes now. So those original airplanes were not as efficient. They didn't run as high velocities as the ones now. So did they lift off? Most likely. Were they as reliable? Absolutely not. Absolutely not. One more thing. Hold on. I'm going to give you a break. One more thing. Let's talk quickly about surface tension. This is something that the book now uses. I never used to teach this, but your new book does, so I thought it's a good mention, and you can learn about chemistry. So imagine a small force applied to the surface of a liquid. You need to visualize surface tension as the surface of the liquid being a membrane. Like what's a good example of a membrane? You stand on, it kind of sinks. Jello? You would really sink in Jello. But it kind of sinks below you and then it can push you back up. Ice?
Quicksand, trampoline.
That's what I was saying. It's easy. Thank you. Trampoline. Technically, sure, but that's a bridge structure. So think about a trampoline. A trampoline is a membrane. The top of the surface of a fluid is like a trampoline. When you ever see like little insects walking across a pond, why can insects walk across a pond? Because they have such little mass that even though the area they're touching is very little, it's very low pressure. The very low pressure on the surface allows the surface to kind of have tension in it, like a membrane. If I stand on a trampoline, I'm putting tension in it. If I were to be a tightrope walker, I'm putting tension in the tightrope. Right? When I walk across the tightrope, I'm putting tension in the tightrope itself. It's called surface tension. That's all it is. Okay? You have some homework in this? You have a couple questions. They're not hard. They're conceptual. Make sure to do them tonight. You have a quick break. Come right back to the lab. When you come back in, grab a laptop, please.